Okay, so we're going to be going over three questions, all of which the Nelson grade 12 chemistry textbook gets wrong as their final solutions at the back of the book. Okay, so question 3. Student titrates 40 milliliters of household ammonia. So our ammonia is our sample, and we have 0.04 liters or 40 milliliters. He does this with, or she, with 25 milliliters of 0.5 molar hydrochloric acid. So 0.5 molar and 0.025 liters. Part A wants us to find the concentration of the ammonia solution. Okay, so we can start off by dissociating our hydrochloric acid. So HCl, strong acid, right? It's going to completely dissociate into H plus and our Cl minus ions, right? So this is going to be a 1-to-1 ratio for hydrochloric acid and our hydronium ions. So we know that if we have 0.5 molar of hydrochloric acid, we're also going to have 0.5 moles per liter of hydronium. And that is in a volume of 0.025 liters. We multiply that out, and you should get 0.0125 moles of hydronium. All right, so now let's dissociate ammonia. So we have NH3, we add some water to that, and that goes into ammonium, NH4, plus our hydroxide ions. So as you notice, I put a single arrow signifying that this ammonia, this base, dissociates completely. But we know that ammonia is a weak base. So why is that? Well, as we add hydronium to this solution, hydronium coming from the hydrochloric acid or a titrant, the amount of hydroxide in this little equilibrium over here decreases, right? We add more hydronium, the amount of hydroxide decreases because they react, right? If this is going to decrease, then we have a stress on the system. That stress being in the product side or the right side. And what do we know about stresses on systems? Well, we know that relates to the Chatlier's principle. So if there's a stress on the right, our system is going to shift to the side of stress. So our ammonia is going to shift to the hydroxide, or in other words, our ammonia is going to dissociate. And as we add more hydronium, more ammonia will dissociate, making it act like a strong acid, at least for the total amount of hydronium that we add. But what do we know about this amount of hydronium that we add to this solution? We know that's the perfect amount to completely dissociate this ammonia. Why? Well, because it says a student titrates a 40 milliliter household ammonia solution. So that means that the solution was completely neutralized. We added the perfect amount of hydrochloric acid to react with this ammonia. So that means that 0.0125 moles of hydronium is going to be the perfect amount to completely dissociate this ammonia solution, right? So this 0.0125 moles of hydronium is going to react with 0.0125 moles of hydronium, which is going to cause 0.0125 moles of ammonia to completely dissociate. So we can say this is a 1-to-1 ratio. And we know that we have, if we're going to have 0.0125 moles of hydronium, we're going to have 0.0125 moles of hydroxide, and we're going to have 0.0125 moles of ammonia. And they want the concentration of the ammonia solution. So if we originally had 0.0125 moles of ammonia, that means that our concentration is going to be that over the original volume of this sample. So that is 0.04 liters. Therefore, our concentration of ammonia is 0.3125 molar. So that is the concentration of ammonia. Okay, so part B wants us to find the pH at the equivalence point. Okay, so what do we know? We know that our hydrochloric acid is going to react with our ammonia. And of course, there's going to be some water in this solution. You don't have to write this. You can if you want. And we're going to form a salt. What's that salt going to be? Well, it's ammonium chloride, right? And we know that our salt is also going to have some water with it, right? So plus H2O. Okay, so now the question is, what is the concentration of this salt that we just formed? Okay, so we know that 0.0125 moles of hydrochloric acid is going to react with 0.0125 moles of ammonia, right? 0.0125 moles of hydronium is going to completely react with 0.0125 moles of hydroxide. It's hydronium coming from the hydrochloric acid, the hydroxide going back to our ammonia. So if that's true, then we're also going to have 0.0125 moles of this salt. So we're going to have 0.0125 moles of ammonium chloride. And that is going to be over the total volume, right? Because we're mixing these two solutions. So we're also mixing their volumes. So it's going to be over 0.065 liters. So your new concentration, or the concentration of the salt, should be 0.192 molar of NH4Cl. Okay, so what type of salt is this? This is a acidic salt. Why? Well, because this Cl ion, it comes from a strong acid, so it's going to be a very, very, very weak base. However, this ammonium ion, it comes from a weak base, but it's still going to be a pretty weak acid, but it's going to be strong enough to dissociate or hydrolyze with water. It's going to be strong enough to react with water, unlike this chloride ion, which is not going to do anything with water. So when we react our ammonium chloride plus water, this chloride becomes useless, right? So what we end up forming is our ammonia ion, and hydronium, right? This ammonium donates a H plus to the H2O, converting that into H plus or H3O, and we're left with ammonia, its conjugate base. So let's write our ice table. So our initial amount of ammonium, or the ammonium ion, which comes from the salt, right? Of course, we stated that the Cl, it's pretty much useless. It's a spectral ion. So we have 0.192 molar minus X, 0.192 minus X. As for the H2O, that's a liquid, so concentration is not going to change. For the ammonia, we have zero initially of hydronium. So we have plus X, X and X. You rearrange the equation, right? X equals the root of Kb, or Ka in this case. Ammonium is the acid, so that times the initial concentration of, well, not the initial concentration, the equilibrium concentration, but we established, or I guess I haven't established, but right, the X is negligible because of how small the Ka is compared to the initial concentration. So we can just say times 0.192. And I guess I should give you guys the Ka, that being, so the Ka equals 5.8 times 10 to the negative 10. So as we can see, this Ka is significantly smaller than our initial amount, meaning this X value, or this minus X, is not going to contribute to anything. It's going to be so small that 0.192 minus X is not going to change, right? So our X, what do we know about our X? We know our X is also equal to our hydronium, right? So our hydronium is equal to the root of 5.8 times 10 to the negative 10 times 0.192, leaving us with a hydronium concentration of 1.056 times 10 to the negative 5 molar. And we know that our pH is equal to the negative log of our hydronium. So negative log of this guy over here. And we end up getting a pH of approximately 4.98, which makes sense, right? We formed an acidic salt, so it's going to produce more hydronium in the solution, making the pH at equivalence point, or after the titration, a little less than 7. I guess is quite a bit more or less than 7, but it's a reasonable amount, and it makes sense, and it adds up with our acidic salt properties. But yeah. So question 4, it's pretty much the same thing, except this time we're working with a acid as the sample and a base as the titrant. So acetosalic, I'm not even going to try to pronounce that, acid is a pain reliever, also known as aspirin. It can be denoted as ASA, so we can write that as ASA. It is a weak acid with a Ka of 3.2 times 10 to the negative 4. Okay, so one aspirin tablet was grounded up and dissolved in 25 milliliters of water. So that was in 0.025 liters of water. The concentration of it, well, that's what they want us to find. And it was titrated with 0.15 molar sodium hydroxide, so NaOH, 0.15 molar. And to reach the endpoint, or equivalence point, it took 98.3 milliliters of base or sodium hydroxide or titrant, so 0.0983 liters. Okay, so now we're just going to be pretty much doing the same thing as the previous question. So our sodium hydroxide, that complete dissociates, right? It's a strong base into Na plus OH minus, 1-to-1 ratio. So we also, that means we have, okay, so I just noticed I made a little mistake over here. This should be concentration and this should be volume, right? So this is 0.15 moles of OH minus per liter times 0.0983 liters, right? That's the volume in this titrant. So we end up getting 0.0147 moles of hydroxide. Okay, and what do we know about this 0.0147 moles of hydroxide? That's going to be the amount that's going to react with the moles of our hydronium produced by our aspirin, right? So that's going to equal the moles of hydronium, which is also going to equal the moles of this aspirin, or at ASA. Okay, so let's dissociate aspirin. So ASA, right, we add some water to it. I'm just going to add water so I can show you what's going on, even though you don't have to do that. It's going to act like a strong acid due to the Chalier's principle that we explained earlier. So, right, it's an acid. It's going to donate a proton. So we're going to have H plus or H3O. And because we donate a proton or hydrogen ion, we're going to be left with one less ion. That's why we put the negative charge. So ASA minus, right? As we showed over here, this is all a 1-to-1 ratio. So we have 0.0147 moles of hydroxide. That's going to react to 0.0147 moles of hydronium, which is going to be the amount of ASA that associates. So we can say we have 0.0147 moles of ASA per, well, they want the concentration, right? So per 0.025 liters, that being the volume of the sample. So we're left with 0.59 molar or moles per liter of ASA. Okay, so part B, they want us to find the amount of ASA that was present in the tablet. So B, well, we kind of already did that, right? It's 0.0147 moles, right? 0.0147 moles of ASA. When they ask for amount, that could be either in moles or grams. So I guess we just leave the answer in moles, right? So 0.0147 moles of ASA. Okay, so part C, they want us to find the pH at the equivalence point. All right, so we just do the same thing as the last question, right? So ASA is going to react with sodium hydroxide to produce a salt. That salt being sodium ASA plus water, right? So this sodium ASA, we know that the sodium comes from a strong base. So it is the weak, very, very weak conjugate acid. It's not going to hydrolyze water. By hydrolyze, I mean it's not going to take or donate an H plus, right, from this H2O molecule, right? This Na is going to be a spectator ion. It's not going to do anything. But this ASA, well, I guess I should put ASA minus, right? This ASA minus is the conjugate base of this weak acid. But it's still going to be pretty weak, but strong enough to hydrolyze water and actually do something to our hydronium concentrations, or in this case, hydroxide concentration. So let's create a nice table, right? So ASA minus, that's going to react with water. Remember, you don't have to show the water. I'm just doing that for convenience. So ASA plus water goes into ASA plus, or just ASA, right? Back to its conjugate acid, plus hydroxide, right? This guy is going to take an H plus, or a proton, making the charge 0 or neutral, and leaving us with an OH, or hydroxide ion. So ice, initially what do we have? We have 0.59 molar minus X, 0.59 minus X, right? Does not change, H2O does not change, 0, 0, plus X, X, X. I'm sure you guys know where to go from here. All we need is the K B. So the KB is 3 points. Okay, so we have a KA, so find the KB. So KB, let's do this in pink. So KB equals KW over KA. So that being 1 times 10 to the negative 14 over KA being 3.2 times 10 to the negative 4. So KB, that should equal 3.125 times 10 to the negative 11. Okay, so I'm going to go pretty fast over here, right, because this is pretty repetitive. As we can see, this KB is a lot greater, or a lot smaller than this 0.59, so it's not going to make a difference. We can say that X equals, if we rearrange the equation, the root of KB times our ASA concentration, or ASA minus, at equilibrium. So we can say our pH equals 14 plus log of the root of our KB, so 3.125 times 10 to the negative 11 times our concentration of our ASA minus at equilibrium. So that is 0.59. Right, remember this guy over here, this is our hydroxide concentration, ROH minus. Plug that all into your calculators and you should get a pH equal to 8.3. So that makes sense, right? We form a basic salt, meaning the amount of hydroxide in this sample, or this titration, once the equivalence point is reached, is going to be greater than the amount of hydronium, meaning that the pH will be greater than 7. And this adds up, right, with our basic salt properties this time. Okay, so this is going to be a different type of titration problem. In this case, we're working with a titration that does not involve the equivalence point, meaning that we have to find the pH of this neutralization reaction before or after the equivalence point. And I'm just going to tell you right now, it's going to be before the equivalence point. So that means our solution is going to be dilute, meaning we can add more titrant to reach that equivalence point, or perfect neutralization. All right, so what is our titrant? So our titrant is sodium hydroxide, right? So 0.5 molar of that. So we have 0.5 molar of that and 0.01 liters of sodium hydroxide. What is our sample? Our sample is hydrocyanic acid. What is our volume of that? That's 0.03 liters, and concentration 0.34 molar. Okay, so when working with these type of problems, we want to set a before and after statement. A before statement telling us the amount of moles of hydronium and hydroxide before the titration began, and an after statement telling us the amount of moles of hydronium and hydroxide after the titration, right? Because this is not a perfect titration, we have not reached the equivalence point, meaning the ratio is not going to be 1-to-1. All right, so before, right, we have sodium hydroxide, complete dissociates, strong base, to sodium plus ROH, right? 1-to-1 ratio, pretty similar to the previous questions. So 0.5 moles of this guy, of hydroxide, per liter, times the amount of liters in this titrant, so 0.01 liters. And we should get 5 times 10 to the negative 3 moles of hydroxide. Okay, so how about our hydronium concentration? So we get that from our HCN, which is going to act like a strong acid due to Le Chatelier's principle, as we said it before, 1-to-1 ratio, right? So if we had 0.34 moles of hydronium per liter times the volume of the sample, so 0.03 liters, we should get 0.0102 moles of hydronium before the titration or the reaction began. All right, so let's do our after statement. So we know that 0.0102 moles of hydronium is greater, so we put that first. So minus 5 times 10 to the negative 3 moles of hydroxide, and we should get 5.2 times 10 to the negative 3 moles of hydronium. So what does that mean? That means that 5 times 10 to the negative 3 moles of hydroxide reacted with 5 times 10 to the negative 3 moles of hydronium, leaving us over with 5.2 times 10 to the negative 3 moles of hydronium that was left unreacted. If this is unreacted, then that means that this amount did not apply to Le Chatelier's principle. There was no hydroxide that was reducing this H+, causing this HCN to dissociate any further. So this 5.2 times 10 to the negative 3 moles of hydronium is also equal to 5.2 times 10 to the negative 3 moles of unreacted hydrocyanic acid. All right, but if you remember, when we react our sodium hydroxide and our cyanic acid, hydrocyanic acid, we form a salt, right? So 5 times 10 to the negative 3 moles of hydroxide reacts to 5 times 10 to the negative 3 moles of hydronium. Hydroxide coming from this guy, hydronium coming from this guy, and we create a salt. So we have HCN, hydrocyanic acid, plus sodium hydroxide, and we form a salt, so that being sodium cyanate, so NaCN, plus water, of course, and this is a 1-to-1 ratio, so 1-to-1 to 1. So if we have 5 times 10 to the negative 3 moles of hydroxide, we're also going to have 5 times 10 to the negative 3 moles of this sodium hydroxide, and that's going to be the same amount of this hydrocyanic acid, which is going to be the same amount as this salt that we form, so sodium cyanide. So that being 5 times 10 to the negative 3 moles of sodium cyanide. Once again, this Na, it's a spectator ion. It's not going to react or hydrolyze with water, right? This is a basic salt. This Na comes from a strong base, meaning it's going to be very weak. This Cn comes from a weak acid, meaning it's still going to be pretty weak, but it's going to be strong enough to hydrolyze with water. It's going to be a strong enough base to hydrolyze or take a H+ or a proton from water. So we're going to include that in our ice table. Okay, so what are the entities in our ice table? So we have ICE, right? We have our hydrocyanic acid. We have some water, of course. We have our conjugate, so Cn minus, or cyanide ion, and we're going to have some hydronium. Remember, this is an equilibrium, right? So we can go either way. We can start with CN plus H2O going into HCN plus OH, or we could go this way, right? I just prefer to go this way. Okay, but for an ice table, we're going to need the molar amounts. So we're going to divide. So let's find the hydrocyanic acid molar amount first. So that's this guy over here. So we're going to divide that by the total volume. So the total volume being 0.04 liters. For the concentration of our hydrocyanic acid is 0.13 molar. 0.13 molar. Now let's find the concentration of our cyanide ion. So that's this guy over here. So we're just going to divide him by, so divided by 0.04 liters, right? And let's bring it over here. So the concentration of our cyanide ion, that equals 0.125 molar. So although the question does not ask for it, if you notice, these concentrations are pretty close to each other. The ratio is approximately 1 to 1. And what do we know about 1-to-1 ratios between an acid or a base and its conjugate pair? Well, that's what a buffer is known as, right? When the HCN and the CN concentrations are approximately equal, then we form a buffering region, meaning that if we add more acid or if we add more conjugate base, the pH is barely going to change. So that means that our pH is going to approximately equal our Ka value, or the negative log of our Ka, right? Because this is going to be an approximate 1-to-1 ratio. However, that is not what the question is asking. It was just a quick little scope into how buffers and the buffering zone works. So let's set up our ice table. So initial, we have 0.13 molar of this guy minus X, so 0.13 minus X. This H2O does not change, and we have 0.125 molar of this guy, so minus X, so 0.125 minus X, and our hydronium is what we're trying to find. So this is 0 plus X, and this is X. What is the Ka for this guy? Alright, so our Ka is equal to 6.2 times 10 to the negative 10. And clearly that is a lot smaller than 0.125 or 0.13, so we can cancel out these x's. And we just solve for x, right? So K equals 0.125x all over 0.13. Notice how this is around a 1-to-1 ratio, right? So if we wanted to, you could cancel these guys out, and we can say Ka equals x, or x equals 6.2 times 10 to the negative 10, which is the proof for a buffer, right? However, we're going to give the exact result for more accuracy, right? So 0.13 Ka is equal to 0.125x. So x is equal to 0.13 times Ka all over 0.125. I'm going to bring the Ka down here. So let me just put this in my calculator real quick. 6.448 times 10 to the negative 10, right? See how close that is to our Ka? We didn't really have to change that much, but for accuracy, of course, we're going to solve for x, right? And what do we know about our x? Our x is also equal to our hydronium concentration. So our hydronium equals 6.448 times 10 to the negative 10. And then pH is just the negative log of that, right? Negative log of hydronium. So the pH is equal to 9.19 approximately. So at 9.19, we're at the buffering zone. So if we want to draw a titration curve, right? This is our little titration curve. over here is 9.19, and it looks something like this, right? We're not really moving that much. And then after the buffering zone, so this is the buffering region at 9.19 being approximately where the perfect buffering zone is. So at the buffering region, if we add more hydronium or hydroxide, the curve barely rises. But after this buffering zone, there's a dramatic change, and that's where we reach the equivalence point, right? However, that is beyond the scope of this question, and it is just asking for the pH. So the pH of this titration is 9.19.